Hello everybody and welcome to chemistry class with your teacher, Mr. Fabianski. If you just give me 1 second, I just got to finish styling my hair. It doesn't look like this on its own. Trust me, it takes me many hours to make it look this short and gray. Yeah, it's a work in progress. Anyway, on today's video, we are going to travel to the late 1800s, the late 18th century, 1700s, late 1700s, and we are going to visit the foundations of the atomic theory. We're going to visit Antoine Lavoiser and his thoughts and why he was considered the father of modern chemistry. So, sit back, enjoy, take some notes, because we're going to go on a journey through chemistry.
Hello everybody, great to have you back. And I want to welcome you again to your chemistry lecture notes. And today we're going to be talking about the foundations of atomic theory, as you saw from the entrance to the video, all about Antoine Lavoisier and other cool, innovative scientists who are doing stuff way before their time. And thankfully for them, you get to sit in that seat right over there and study chemistry. So without further ado, let's start this stuff. Move myself down over here and let's continue to take a look. Now, for as long as we are teaching about this, you cannot forget Democritus. You can't forget Aristotle. They had the visions that were way before their time, but it's important to remember where you came from. Without their visions, the scientists that we learn about today, I don't know if they would have been able to conduct the experiments, to have the thought processes that they had. So you can't forget where you came from. So, let me set the stage. Late 1700s, late 18th century, chemistry, just coming alive again. We have definitions for an element. It's a substance that cannot be broken down any further by any chemical means. The elements on the periodic table, you know, those elements.
Over there, right? On that periodic table right there.
I'll try and do a zoom cut to the periodic table in my post-production editing. Hopefully you guys are going to keep me honest with that. The law of conservation of mass. Law of conservation of anything. Mass, matter, energy, momentum. It's always, whatever it is, mass, matter, energy, momentum, can neither be created nor destroyed, only transferred, only transformed. Okay? So no difference with the law of conservation of mass here. Mass can neither be created nor destroyed, only transformed. And then the law of definite proportions, or the law of law of constant composition. Take water, for example. It's H2O. No matter where your H2O is, if it's here, if it's in France, if it's in England, if it's in Texas, if it's in Arkansas, it's always H2O. Whether you have a little droplet or 5,000 gallons, it's always going to be H2O. All right? That's the law of definite proportions. That's the law of constant composition. Continuing to move on. Actually, I do want to show you a little bit more on that conservation of mass. So we're going to cut to a quick commercial clip here, brought to you by Fabianski Science Chemistry Center. And I will see you guys when we return.
Hello everybody and welcome to this quick commercial break. In this commercial, or in this little segment, I would like to explain to you guys a little bit about the law of conservation of mass. Here is a skewer. I'm going to turn on this light. Here is just a regular barbecue skewer made of wood. If we were to take a mass of this, let's say that it would weigh 10 grams. Now what we're going to do is light the wooden barbecue skewer on fire. Okay? Now as this is burning, it is releasing gases. Okay. If we were to allow this to completely burn and then re-weigh what is left, you would agree that we would not get those 10 grams back. However, it was deemed that if we weigh everything that's left over, along with the gases that were released, that we would still retain those 10 grams. That's the law of conservation of mass. Okay? Capturing everything, the gases, what's left over, and measuring that would then allow us to understand that mass can neither be created nor destroyed, only transferred or transformed from form to form. That is the conservation of mass. The atoms in this wood didn't just disappear. They just went into the gaseous state. But they're still atoms. They still exist. They still have mass. Thank you for joining me in the fume hood. That is what we just did our little experiment in. The fume hood here in the classroom. So, and with that, we'll take it back to our host for the remainder of the PowerPoint. Take care.
Welcome back. I hope you enjoyed that little intermission, and hopefully you enjoyed the commercial. I hear it was a pretty darn good commercial. So yeah. So anyway, let's continue. Antoine Lavoiser. It's a fun name to say. He was a French nobleman. He was very wealthy, had a very wealthy family in Paris in the 1700s, and for that reason, he was able to purchase some of the best scientific equipment of his time, some of the most precise and accurate scientific equipment. However, on the downside, he was convicted of some crimes, and due to this, he lost his head to the guillotine. But we can't forget all the amazing discoveries of chemistry that he made before his passing. He was truly a revolutionary thinker. Looking a little more in depth into Antoine Lavoisier, and you remember this picture from before, he is considered to be the father of modern chemistry. And think, although matter may change its form from shape to shape, it's still retained in the mass. Now, you may know this as the law of conservation of, drum roll please, law of conservation of mass, right? Okay. Mass, think back to the commercial. Mass is neither created nor destroyed. Objects, the atoms still remain the same. Antoine Lavoisier also came up with an extensive list and named many elements, which included oxygen and hydrogen. And I'd like to show you at least one of these videos. It's the first video. Remember, this PowerPoint is located in the Files tab of your Teams class, so you can go in and you can watch those other 3 videos if you choose to do so. But I'd like to show you that video quick. So I'll see you right after this, yet again, commercial break.
Matter is a complicated matter. In ancient Greece, Aristotle stated it was made from fire, water, air, and earth. His theory was accepted for 2,000 years, but now we know it's made of more than 100 elements. So how did we change our way to see it? It's 1772, and a Parisian named Antoine Lavoiser is working to improve the gunpowder. And so he studies how combustion works. At that time, people believed that a fire-like fluid called phlogiston was trapped within all matter, and burning meant setting the phlogiston free. That was why after burning, objects weighted less. Working together with his wife Marianne Pauls, he designed a sealed vessel. Taking careful measurements, they put inside phosphorus and combusted it. The weight of the vessel was the same before and after because nothing had escaped. That was fine. But the matter left inside the vessel after the experiment, it weighted more than it did before. If the phlogiston theory was correct, it should weigh less. Unless air wasn't only air. What if air was made of different gases that could join other substances and make them heavier? Lavoisier had heard the experiments of Cavendish, who synthesized water by mixing 2 different gases he called inflammable air and dephlogisticated air. Lavoisier set himself to confirm Cavendish's findings. He removed the air inside a vessel with a vacuum pump and let both gases flow in. An electric spark ignited the combustion and, voila, water started to form. Lavoisier proved that water was no longer an element, but a compound made of two elements that he named hydrogen and oxygen. That was a revolution. Air, water. The four classic elements were just combinations of brand new elements that should be identified and described separately. Supported by his wife and scientists who believed him, Lavoisier started that search. They identified 55 elements and found a systematic way to name them. He condensed all his work in the first chemistry textbook ever that contained three simple ideas. Phlogiston doesn't exist, the matter we see is made of elements, and that matter isn't created or destroyed. It merely transforms through chemical reactions.
And welcome back. We're just going to go through a couple more of these slides, and then from there, I think we will cut this one short. All right, so here the next slide is the law of multiple proportions. We remember back from the law of constant composition. If you had water, it was H2O, and it was going to be H2O regardless. It would always be two hydrogens to one oxygen. Here, law of multiple proportions means that when you have two elements from a series of compounds, the ratios of the masses of the second element combined with 1 gram of the first can be reduced to small whole numbers. All right, so what exactly does that mean? Well, let's take a quick look. For example, water. Water has a mass ratio hydrogen to oxygen of 1 to 8. Okay, meaning that water, when compared, its mass compared to oxygen, is a 1 to 8 ratio. Hydrogen peroxide, still made up of hydrogen and oxygens, has a mass ratio of 1 to 16. Okay, the mass ratio of the second element, the oxygens, when comparing water and hydrogen peroxide, is an 8 to 16 or a 1 to 2 ratio. That's the law of multiple proportions. Okay, you're taking water, you're taking hydrogen peroxide, you're taking two elements that both just involve hydrogen and oxygen, and you're looking at the ratios of the second element, oxygen in this case, and comparing those, 8 to 16 or 1 to 2. Continuing with our development of the atomic theory, we come to my man, Dalton. Dalton's atomic theory. This was the guy that started putting everything all together. See, early in the 19th century, John Dalton, he was a school teacher, much like your famous chemistry teacher from Putnam High School, Mr. Fabianski. That would be me. I'm sure I'm well known throughout the YouTube community. Probably not. In fact, you guys, my class, are probably the only ones who are watching this. But if you are watching this from somewhere in a land far, far away, welcome, and I hope you are enjoying it. Anyway, John Dalton, a school teacher, he explained the laws of conservation, definite proportions, and multiple proportions, and he explained why those laws were true. Okay? Why they were true by proposing that elements were composed of atoms. He is taking all of these laws that were true, and he's saying the reason they're true is because elements are composed of atoms. Okay? So think about that. Atoms and molecules. This is Dalton's new way of chemistry. Okay? His atomic theory. He's saying that, and that's essentially right there in your screen. Oh, over there, sorry. Over there in your screen. Actually, I'll just bring myself right up over there. Here I go. Walking on over. Right there. Nope, right there. Man, this is harder than I thought. Right there. There we go. Hopefully you guys are getting a good laugh out of this. Right there. That's his periodic table. Okay? Atoms and molecules are shown by using Dalton's new system of chemical philosophy, classifying these atoms, molecules, compounds in a way that was known at the time. So, for something to be a theory, we have to have a set of rules to follow, and these rules have to be proposed and they have to withstand time. And that's exactly what Dalton's atomic theory did. He proposed these rules, and they were supported and they withstood time. And what I would like to show you now, down here again, is Dalton's atomic theory. He had 5 components to the atomic theory. 5 components. 1. All matter is composed of extremely small particles that we call atoms. 2. Atoms of a given element are identical in terms of size, mass, and other proportions, meaning the atoms of, say, water, the hydrogen atoms of water, are identical. All hydrogen atoms are identical. Atoms cannot be subdivided, created, or destroyed. Atoms of different elements combine in simple whole number ratios to form compounds. And in chemical reactions, atoms are not subdivided, created, nor are they destroyed. Now, we realize that we can further Dalton's atomic theory, but given the time, this was an amazing set of 5 guidelines. So these 5 set of principles of guidelines for Dalton's atomic theory, totally ahead of their time, totally revolutionary, unbelievable. Now, are all the pieces of Dalton's atomic theory correct today? Should they be modified? We'll take a quick look back. I mean, what are some things that definitely pop out to you? I'm thinking number 3, maybe number 5. We know that atoms can be subdivided. We know that we can look at protons, neutrons, and electrons. We know we can look at quarks. For number 5, we know of nuclear reactions where the atoms are broken down. We have nuclear decay, alpha radiation, beta and gamma radiation. We know neutrons are ejected. Okay, different atoms can be made through the breakdown, through the decay of other atoms. We have isotopes. We have ions. All of these things can be modifications to Dalton's atomic theory. But remember, at the time, unbelievable. All right, everybody. Well, I hope you've enjoyed that little piece of PowerPoint. Please join me next time. We're going to continue to move on with this PowerPoint, get into a couple more atomic models, and further our knowledge of the atomic theory. All right, until next time, I will see you all. Enjoy your day, and take care. And let the music take us out.